Okay. Good. All right. Welcome back, everyone. Okay, this mic is working. Yes, this mic is working very well. Okay. Oh, this mic is working too well. Okay, so good morning, everyone. So welcome back to Company 30. As I just said, this is lecture 22, which is very exciting because 22 is a palindrome, which I'm sure you've grown very fond of by now. So before we get to today's material, I'd like to give you the Italian expression of the day. So today's Italian expression is the following. It's a rather involved one this time. So it's prendere lucciole per lanterne, which means to mistake or to confuse fireflies for lanterns. Oh, you already knew what it meant? It means to mistake fireflies for lanterns. You know, so fireflies are these insects that fly, and at night they light up. And so if you have a whole bunch of fireflies, then maybe you can mistake them for a lantern. And so the actual figurative meaning of this expression is to mean something like to confuse one thing for another. So what's an example of a sentence in which I use this and it's somewhat relevant to you? In this case, it's extremely relevant to you. So this is my sentence. Cesare has purposefully added the instruction read carefully in assignment 5 and also assignment 6 and also the final exam, so that students don't prendono lucciole per lanterne. So make sure to read the instructions carefully, especially in the final exam. Okay. The other thing I wanted to talk about was how do people feel about assignment 5? Okay, then no extension then. Well, because no one said anything. Do you want an extension? Yes. If I gave an extension, I'm gonna make assignment 6 due December 5th anyways. So I can give like 1 day. 1 or 2 days? Okay. Sunday. I'll make it due Sunday. Okay, so that ruins your weekend. But if you want, I can do that. Okay, so I will extend assignment 5 to Sunday at midnight. Okay, and I will release. Oh, hello. I will release assignment 6 on Friday regardless because it's already ready. So if you've already finished assignment 5, then you can already start assignment 6. Okay, good. All right. So now we can get to today's material. So today's material is going to be a continuation of the characterization of undecidability. Okay, so this is 2 because it's the second time we're talking about this. And so to refresh your memory about what we were talking about on Tuesday, I just want to show you essentially the last notes that I wrote down on Tuesday's class, so you don't have to panically write this because hopefully it's already written. So how we had ended Tuesday's class, what we were saying is that we have these undecidable problems. So we proved that some problems are undecidable, but they're different levels of impossible. Right? So for instance, the halting problem is undecidable, but it's CE or Turing recognizable, meaning that you can check yes instances. So that means that if a priori I give you an instance of the halting problem, which you know is yes, for which you know the answer is yes, then you can check it. How do you check it? Well, just take the Turing machine and run it on the input string, and at some point it'll halt, right? And then on the other hand, we have undecidable problems like the emptiness problem, which are undecidable, but they are co-Turing recognizable or co-CE, meaning that you can check no instances. Okay, and so we'll see how we can do that today. And then finally, we have this class of even more undecidable problems. So they're doubly undecidable. And that's because you can neither check a yes instance nor a no instance. And at the end of today's class, we'll see how we can prove that a problem is neither CE nor co-CE. Okay. So what I've started to do, though, is I've started to use Turing recognizable and CE interchangeably. I've started using these terms interchangeably. So it's true that I can do this, but there's actually a theorem that tells me that I can do this. And to introduce that theorem, I need to talk about something very special, known as an enumerator. So the notion of an enumerator is what allows me formally to define this notion of computably enumerable. So you're probably thinking, well, what is an enumerator? So an enumerator is a computational model very similar to all of the other computational models we've seen so far in this class. So it's composed of, you probably guessed it, a control unit. So the control unit has a start state, a single unique start state, and it has this very special state called the enumeration state. So the enumeration state. And along with the control unit, the enumerator has two tapes. It has a work tape and it has an output tape. And the way the enumerator works is it starts at the start state and it does its thing, it goes through the control unit's transition diagram, and perhaps maybe at some point it gets to the enum state. Once it gets to the enum state, whatever the enumerator wrote on the output tape gets enumerated. So for instance, maybe the first string that the enumerator wrote onto the output tape when it got to the enum state was, I don't know, ABB. So ABB is on the output tape and the enumerator has reached the enum state. And so at that point, the enumerator enumerates ABB. So it enumerates ABB. So this is, say, the first string enumerated by E. So let's call this enumerator E. E for enumerator. Okay. And then at that point, it erases its output tape. It erases its output tape and it starts back over, but it doesn't start back over from the start state. It starts back over from the enum state. So maybe, it keeps doing its thing. It keeps going and then it comes back to the enum state once again. Once it comes back to the enum state, maybe it's written something like BAA. So it's at the enum state and it's written BAA on the output tape. And so it enumerates BAA. So this is the second string that's enumerated by E. And then the enumerator keeps going. Okay, so it keeps going. And so now you're probably thinking, well, what's the stopping condition? An enumerator is very special because it has no stopping condition. The convention is that the enumerator E runs forever. Okay. So it runs forever. And then we denote L of E. We denote L of E as the set of all strings enumerated by E. So for instance, in this case, the first string enumerated by E would be ABB. The second one would be EAA, and so on. And so for some string WI in L of E, WI is in L of E if there exists some number of finite steps such that at some point the enumerator gets to the enum state while having WI on the output tape. So E enumerates WI in some finite number of steps. Okay. And it's very possible, right? So it's very possible that an enumerator doesn't enumerate a string, right? So it's not necessary that L of V is equal to sigma star. It could be only a single string, or it could be multiple strings. So for instance, ABA could not be enumerated. So ABA could not be enumerated. And it's also possible for a string to be enumerated multiple times. So for instance, ABB could be enumerated maybe once here, and then once here at the 17th string. So ABB could be enumerated multiple times. And the other thing that's possible is because it turns out an enumerator is equivalent in computational power to Turing machines, it introduces loops, and thus it introduces the possibility of an infinite loop. So what could also happen is in my enumerator E, I could have some infinite loop at the very beginning. So then E could loop forever at the very beginning, and it would never enumerate any string because it could never get to the enumeration state. So then it's also possible that L of E is equal to the empty set if E is in an infinite loop and never reaches ever reaches the enum state. Okay, so that's an enumerator. I won't give more details than that in terms of the formal tuple definition, because that would just be a waste of time. The idea of what an enumerator does is good enough for our purposes, and so the formal definition I'll give you won't be all that formal, really. I'll just rewrite what I've kind of explained so far. So consider some non-empty alphabet. Then we say that an enumerator E is a computational model which enumerates. So this is the key term, enumerates strings in sigma star 0 or more times. Okay. And there's the additional restriction. There's the additional restriction that we say that E runs forever. Okay. So that's just written down the high-level definition that I gave you. The high-level definition is good enough. Just knowing that an enumerator enumerates strings is good enough for our purposes. And so then formally, L of E, well, semi-formally, I should say, is the collection of all strings for which these strings are enumerated by E in a finite number of steps. Okay, that's L of E. And so now we're actually very well placed to properly define what CE means instead of just saying, oh, it's a synonym. So the proper definition of CE is if we're given some non-empty alphabet and some language defined over that non-empty alphabet, then we say that L is computably enumerable, also known as CE, if there exists an enumerator E which enumerates it, such that L of E is equal to L. Okay. That's an enumerator. And that's the definition of computably enumerable, which now makes sense. Enumerable enumerator, that checks out, I think. Okay. And so now we're ready to state that the notion of computably enumerable is truly a synonym, quote unquote, of Turing recognizable. Really, what this means is that Turing recognizability and computably enumerable languages, they talk about the exact same family of languages. Okay, so that's what I'll state in the following theorem. So suppose I have a non-empty alphabet and I have some language defined over that alphabet. Then we say that L is CE if and only if L is Turing recognizable. So the idea is that accepting strings with a Turing machine is equivalent to enumerating those strings with an enumerator. And so to prove this, what we're going to do is we're just going to simulate an enumerator with the Turing machine that accepts the string and vice versa. Make sense? And so I'm actually going to prove this because the ideas in this proof are quite important. They introduce a new sort of algorithm design technique, if you really want to call it that, known as dovetailing. So we're not going to get to dovetailing right away. We're going to do the easy direction first. And it turns out that the easy direction is this if-then. So in this if-then, I assume that L is CE. And so by definition, that means that there exists some enumerator E such that E enumerates L. Okay, that's by definition, right? I have an enumerator which enumerates L. And so now what I want to show that L is Turing recognizable. Right? So what I want to show is that L is Turing recognizable. I'll just write recognizable. And so to show that, well, I need to design a Turing machine M such that L of M is equal to L. Okay. So that's what it means for a language L to be Turing recognizable. It means that there is some Turing machine M which accepts it. And so how am I going to do this? Well, I need to use what I have in my hypothesis. And what I have in my hypothesis is that I have an enumerator which enumerates L. Okay, so here's an idea. Here's an idea. The Turing machine M, which I want to design, it just takes some string and it runs E, and it just checks if the input string at some point is enumerated by E. If yes, then it accepts. Otherwise, the Turing machine just waits. Okay? And so it loops forever, and that's okay, right? Because remember, for a Turing machine M to accept the language L, it has to accept all the strings in L and only all of the strings in L. And doing what I just described does indeed do that. So let's describe N slightly more formally. So M is going to, on input W, going to run E. Okay, so it doesn't really matter how exactly it does this. You can imagine that M creates multiple tapes. It places the description on E on one tape and the output and work tape on the other tapes, and it just simulates E. So it just runs E. And what M will do is for every string that's enumerated, for each string enumerated, for each string which is enumerated by E, let's call that string X. Let's check if W, so W, remember, W is the input to M, right? So these are the same thing. Check if W is equal to X, right? So I'm checking if my enumerator did enumerate the string X, the string W, pardon me. Okay. And so if yes, then my Turing machine M will accept. If not, it just keeps waiting and it just keeps checking the enumerator, right? So maybe the enumerator doesn't enumerate any strings, in which case L of M is empty, but that must have meant that L of E was also empty. And L of E is equal to L, so I have that L of M is equal to L, right? And so I have that L of M is equal to L because any string which is enumerated by E will be accepted by M, and all the strings enumerated by E are in L, and those are only the strings in L. So I have this equivalence, and so that works out. So I'm not going to write down the formal proof of correctness. I'll do that later, but what I just said is good enough. So I'll post in today's class. I'm going to have to skip through some of the proofs, unfortunately, but I'll post them later to make everyone happy. Okay. So that's the first direction. Any questions about the first direction? No, doesn't look like it. So let's do the second direction, which is harder. And it requires introducing a new technique, which is exciting. New techniques are fun, especially when I have fun names like dovetailing. No? Okay. Okay. So in the other direction, I'm assuming that L is recognizable, and I need to show that it's CE, right? So I assume that L is recognizable. And so therefore, I have some Turing machine M such that L of M is equal to L, right? That's just by definition of what it means for L to be Turing recognizable. Okay, and so now what I want to do is I want to show that L is CE. And so to do that, well, by definition, I need to design an enumerator E such that L of E is equal to L. Okay, right? That's what I need to do. That's what I need to do to show that L is CE. Okay. So here's a idea. It's going to be a naive one, but I know that I have my Turing machine M, which accepts L, right? And so to create an enumerator E, which enumerates all the strings in E, well, what if I just go through each of the strings in sigma star, and I run M on each of those strings. And if M accepts, then I enumerate. Otherwise, I just keep going. Doesn't sound problematic. Let's write that down. So let's write that down. So let's create the enumerator E, which does the following. So for every string in sigma star. And so let's assume that sigma star is in lexicographic order, right? So it's sorted from the empty string 0, 1, and so on. Right? So it's sorted in lexicographic order. So I have this infinite for loop. That's okay because an enumerator can run forever. So I'm not doing anything illegal. Then within the body of this for loop, I will run m on x. Okay, run m on x. And then if m accepts, then I enumerate. Otherwise, I just keep going. Right? Does this work? Let's see. Louis knows it doesn't work. Anthony, why doesn't it work? Right, very good. Because, for instance, what if the enumerator is extremely unlucky and m loops forever on the empty string? So m loops forever on the empty string, but say m accepts 0. Well, that's unfortunate. That means that E starts by setting x to the empty string. It runs m on x, and it just waits. And it waits, and it waits, and it waits. And it never gets to this line, so then it never gets back to the for loop to reset x. Well, that's sad. That means that this doesn't really work, right? Because that means that L of E enumerates the empty set, whereas L of M had at least one string. So that doesn't work. Okay. But what does work is this technique known as dovetailing. And before I introduce dovetailing, I'll introduce the general idea of what it's supposed to do. So the general idea of what it's supposed to do is, well, it would be nice, right, if I could simulate M on each of the strings in parallel. If I could somehow acquire infinite parallelism, whatever that is, then I could do something like the following. I could take every single string in sigma star, starting from the empty string, 0, 1, 0, 0, 0, 1, 1, 0, and so on. And you know, this is time step 0, this is time step 1, this is time step 2, 3. And I just run m on each of these strings in parallel, right? Infinite parallelism, amazing. So, you know, m on E runs forever, so this never ends, but maybe m on 0 ends very early. Right? So maybe here it gets accepted. Maybe m on E doesn't run forever, but gets rejected. Maybe m on 0, 0, well, it gets accepted even earlier. M on 0, 1, maybe that loops forever, and so on. So I do this infinite parallelism black magic. And then I say, okay, well, take all the strings that ended at time step 1 and enumerate them. Then all the strings that were accepted at time step 2, and then enumerate them, and so on. Right? Okay, that sounds like it should work. The only problem is, you know, what is infinite parallelism? Do I take the Turing machine and copy it an infinite number of times? I don't think that'll work. And so what I need to do is I need to simulate infinite parallelism. What an interesting idea. We're going to simulate infinite parallelism, which I spelled correctly. Good. Okay. And so I'm going to do that with this technique known as dovetailing, also sometimes called time sharing. Okay. And this technique, essentially the general idea is I'm going to run M sequentially, so in sequence, so not in parallel. I'm only going to have a single copy of M, but I'm going to run M on each string, for progressively more time steps. Progressively more time steps, such that I simulate infinite parallelism. Okay, so what is that going to look like? Well, let's take our running example here. Let me make this a bit bigger. Okay, so what I'm going to do is, you know, let's just copy over the strings I have here. So I have the empty string, 0, 1, 0, 0, 1. And I still have the number of time steps, right? So I have the first time step, the second one, third one, so on. And what I'm going to do is I'm going to expand the input string set that I use to run M on. Okay. And at the same time, I'm going to increment the number of steps I run M on each of those strings. So that sounds a bit abstract and a bit scary. It's not all that scary. Let's see how that works. So at first, I'm going to run M on the empty string for one step. So I run M on the empty string for one step. And then I stop and I check if M accepted the empty string. If yes, I enumerate it. If no, I keep going. So in this case, it's a no because M loops forever on the empty string. And so then what I do is I take the empty string and now 0, and I run both of those on M for 2 steps. So I run M on the empty string for 2 steps and M on 0 for 2 steps. So M on the empty string doesn't accept, so I don't enumerate it. But M on 0 does accept, right? So it does accept, and so this gets enumerated. So I enumerate. And then I do the same thing again. I run M on the empty string 0, 1, but now I do that for 3 time steps. So I do that for 3 time steps. So I run M on the empty string for 3 time steps, the same thing for 0, and the same thing for 1. So M on the empty string doesn't accept, so I don't enumerate. M on 0 has accepted, right? It's accepted early, and so again, I enumerate. It doesn't matter if my enumerator enumerates the same string multiple times, that's fine, right? So again, I enumerate. If I look at 1, well, M on 1 rejected, so I don't enumerate. And again, I keep going, right? I keep going. I increase my input string set by 1 more string, and I increment the number of time steps. So this is the last one I'll do because you seem bored already. So I'll run M on the empty string for 4 time steps. The same thing for 0. The same thing for 1. And the same thing for 0, 0. So again, M on the empty string loops forever, so I don't enumerate. M on 0 does halt and accept, so I enumerate. So what this is telling me is actually I'm going to enumerate 0 an infinite number of times. That's okay, right? M on 1 rejects, so I don't enumerate. But M on 0, 0, well, that accepted, and that accepted even earlier, so it accepted here. And so that means that when I finish this computation, I also enumerate. Okay. And so I'm not actually running these things in parallel, right? I'm first, running M on the empty string. Then I check whether accepted or not. And then I reset M. I reset M in the tape. And I run it on 0 for 4 steps. Then I reset it. And then I run M on 1 for 4 steps, and so on. So I'm not waiting forever, right? So this was the problem with this naive implementation, is that I was waiting forever here. In this case, I don't wait forever, right? I just keep increasing my input string set, and I keep increasing the number of steps I take on every single string in that set. Okay? And so if I want to write that down formally, if I want to write down the dovetailing procedure formally, I could just say something like E, so let me just make this a bit bigger. E is assigned the block of code where it starts with an infinite for loop, which in this case iterates over the natural numbers without 0. And so within the body of the for loop, it's going to run M on strings, let's say W1 to WI for I steps. So this is what I meant when I was assuming lexicographic order. I just meant, I'm ordering sigma star, okay? And then I'm saying, well, the empty string is W1, 0 is W2, 1 is W3, and so on, right? And so this is well defined. Okay. So I run M on strings W1 to WI for I steps sequentially. And then I enumerate every string, W1 to WI, which M accepted. Okay. And so this enumerator does work. It doesn't loop forever. It doesn't get stuck anywhere. And eventually, at some point, it's going to enumerate all of the strings in L and only all of the strings in L. So LV is indeed equal to L. Well, why is this true? If we quickly try to argue this, if a string is enumerated by E, then that means that at some point when E was simulating M accepted that string, and that's the only way that E would have enumerated that string. Right? So I have this one-to-one correspondence between the strings accepted by M and the strings enumerated by E, but L of M is equal to L by hypothesis. And so this is, as we say, all good. Okay. Yeah, you have a question? I thought this was clear. Not clear? What's to stop a string from taking an infinite number of steps on M? Well, I guess it's M that takes an infinite number of, yeah, anyways. But I think the question is, you're given an input string to M, and M runs forever, right? Well, that's okay, right? M runs forever. That means that this condition, right, where M accepted that string is never going to be true, so E is never going to enumerate, right? So it's basically going to pointlessly simulate M on that string forever, but that's okay, right? Because I'm still doing a finite number of computational steps on every string, right? So I'm not getting stuck at any particular point. Yeah? Yes, Jules, yes.
Is creating the lexicographic order part of the algorithm?
Yes, it is. I've just not included it because I'm lazy. But the question was, sorry? Oh, lexicographic order. Yeah, that's compute. Yeah. Okay, great. Excellent. So hopefully that was clear. So this technique, like I just said, is formally known as dovetailing. So, why is it called dovetailing? Well, it's kind of because you're sort of interlocking the computations of M on every string together. Right? And so that's a dovetail. Very good. Okay. And so now you're probably asking, well, what's the point? This is cool, but how can I actually use it? Well, we can use dovetailing to create yes or no verifiers, right? And so we're going to use dovetailing right now to show that the emptiness problem is not, no, it is cosine. Okay. So we can use dovetailing to create a yes or no verifier. Okay. And so we're going to use dovetailing to show that the emptiness problem is cosine. At this point, I'm sort of obligated to tell you what formally cosine means because I haven't told you yet. So formally, the definition of cosine is for some non-empty alphabet and some language over that alphabet, we say that L is cosine if L complement is CE. Okay. But L complement being CE, the intuition is just that if the answer to the decision problem is no, then I can verify it, right? So the intuition is if the answer to the decision problem is no, then I can verify that. Can verify this. Okay. And so that's what we're going to do in the following example. We're going to show that we have a essentially no verifier for the emptiness problem. So we're going to show that empty is co-CE. Okay. So how am I going to do this? Well, let me just quickly remind you of what the language corresponding to the emptiness problem is. So the language corresponding to the emptiness problem, that's just a collection, a set of binary encodings of Turing machines, which is denoted with these angle brackets and then M. where, of course, M is a Turing machine. M is a Turing machine. And L of M, so the language accepted by M is empty. So take all of the Turing machines, right? There's a bunch of Turing machines. Take the ones that don't accept anything and then place them in this set, encoding them as binary strings, right? That's what L sub empty is. And so now if I want to show that empty is co-CE, I need to show that L sub empty complement is CE. So I need to show that L sub empty complement is CE. And so to do this, I need to create, so I'm going to revert back to saying that CE is just Turing recognizable because it's going to be much easier if I just design a Turing machine that accepts L sub empty complement. So I'm going to create a Turing machine N such that L of N is equal to L sub empty complement. You could have also designed an enumerator, but it's much easier to just design a Turing machine which accepts L sub empty complement. So now, what does L sub empty complement contain? Right. Well, the first thing it contains, right, and so this is a subtle point, the first thing it contains is it contains all strings, right, because L sub empty is just a language, so L complement also just is a language, and so it contains strings. And so some of the strings in the complement of empty are the strings which just don't encode a valid instance of the emptiness problem, right? So there's strings that don't binary encode a Turing machine. So the first collection of strings in this set or in this language are invalid instances. Invalid instances of encodings of Turing machines, right? So, you know, the empty string is probably not a valid instance of the emptiness problem because the empty string probably doesn't encode a Turing machine. Actually, certainly doesn't. Okay, but in my Turing machine, if I want my Turing machine to accept L sub empty complement, then this part of the set is going to be pretty easy. I just check whether the input string that I got respects the rules of encoding strings into Turing machines. If no, then I should accept because that means that my input string wasn't a valid instance. And so this is not hard to do. What's hard to do is also accepting this other set, which makes up L sub empty complement, which is the language that contains strings which are valid encodings of Turing machines, and thus valid encodings of the emptiness problem, but where we negate the necessary and sufficient conditions to this language here. Right? So in other words, M is a Turing machine and L of M is not empty. Okay. So this part is not hard, right? Not hard. Just hard code the rules. The rules of creating some binary encoding of M. But this part is slightly trickier, right? Because if I know a priori that I have some Turing machine M, which doesn't accept the empty string, right? Then that means that that doesn't accept the empty set, right? So it doesn't accept, so it accepts at least one string. If I know a priori this, then I need to somehow check it. And so the incorrect thing to do would be to just sequentially run M on every single string, because maybe it loops forever on the empty string, right? And so then I get stuck in my checker. So instead, what I need to do is I need to dovetail M on every single string in sigma star. Because then at some point, one of those strings, because a priori I know that L of M is not equal to the empty set, I know that one of those strings is going to lead me to a halt and an accept. And then I can just say, yes, I do have a no instance. Right? And so that's exactly what I'm going to do. So to do this part, I need to dovetail the computation of M on sigma star. Right? And so altogether, I'm going to create this Turing machine N, which on input W is going to first check if W is some valid encoding of some Turing machine, right? If no, then I can immediately accept, right? I'm accepting because I'm accepting the complement of empty, right? So I can immediately accept. Because of course I have a no instance, this isn't even a valid instance, right? Otherwise, right? Otherwise, I'm going to dovetail, right? So how am I going to dovetail? I'm going to run this infinite integer for loop, where within the body of this for loop, I'm going to have something that's very similar to the previous proof where I used dovetailing for the first time. I'm going to run m on w1 to wi in I steps. Again, assuming that I have some lexicographic order to sigma star. And then if any of these strings that I ran m on were accepted, then I should accept, right? Because that means that L of m accepted at least one string. And so I'm verifying that I do truly have a no instance. Because remember, a no instance means that L of m is not equal to the empty set, which means that I have at least one string in L of m. So if m accepted any string in w1 to wi, then the Turing machine n should accept. And so then the claim is that L of n is equal to L sub empty complement. Okay. So why is this true? Well, if I have some string in L sub empty complement, which is not a valid instance of the emptiness problem, then it immediately gets accepted by n, right? Otherwise, if it is a valid instance, but the answer is no, right? So at least one string is accepted by m, then at some point, intertwining all the computations of m on all the strings, I'm going to get a string that allows m to accept. So then my Turing machine n will then accept, and I'll get that that string was indeed in L sub empty complement. Yeah.
Then here, what is W exactly? Because is it like a string or like a disk? Like, does it run at
Well, this W here, I see. So the question is, I think the question is, what's the difference between this W and this W, right? So this W, right? So that's a good question. This W is the input to the Turing machine. So it's the input to your function, right? And imagine that within your function, you have sigma star, right? You have sigma star, and you can create sigma star in a lexicographic fashion. So you're not actually creating an infinite set. You're just creating the next string that follows, say, the empty string, so that's 0, and then the next string that follows 0, that's 1, and so on, right? So these are strings. So n is actually creating these strings. So n creates these strings. Okay. And it does so in the lexicographic order that I just talked about. Yeah? Okay, good. Any other questions about this? No questions? Okay. I'm happy. Slightly subject. Oh, yes. Okay, good question. Right. Okay, very good. So, yes, good. So, if you run in, very good, excellent question. If you run into a Turing machine, right? So the question is, if you run into a Turing machine that loops on every string, right? So, I checked that the input string was some binary encoding of some Turing machine. It was, and so I go to this otherwise, and now I start running m on every single string. So I'm never going to get that m accepted. So then n is going to loop forever, and that's okay, right? Because m is not a valid instance. M is not a no instance to the emptiness problem, right? It's a yes instance because L of m, right? If m loops forever, loops forever on every string, right? Then that implies that L of M is the empty set, right? Right? So the empty set is a yes instance to the emptiness problem. But my verifier is supposed to check no instances. And so it does that, right? If I have a yes instance, there's no guarantee that I helped. Well, that's fine. Right? You see. But I see. So I think I see. So the question is, why aren't we running all of the machines, right? Well, that's not what you're doing. That's not what you're designing in this Turing machine. This Turing machine is just accepting some input string. And it's just checking whether that input string is in the language L sub empty complement. So because what you're trying to describe, I think what you're trying to describe is the enumerator that would enumerate all of the strings that are valid instances of the emptiness problem and for which there's no answers. That's what you're describing. Yeah. In which case you could do that, right? And it would work. Yeah. So that would be the enumerator for L sub empty complement. Very good. Yeah. Excellent. Good question. Any other questions? No? Okay. Okay. All right. So what this means, right? This means that this shows that the emptiness problem is co-CE, right? Because I can verify no instances to the emptiness problem. So now the question which naturally arises, well, at least to me, is could empty also be CE? Right? As we've shown that it's co-CE, could it also be CE? Well, the quick sort of trick to check if something is CE is you think about the yes verifier, right? So how do I create a yes verifier for the emptiness problem, for the proper emptiness problem? So any yes instance to the emptiness problem, any valid yes instance, is a Turing machine L of M where M does not accept any string. Well, what if, like Anthony was saying, M loops forever on every string? In that case, I can never actually verify that that was a yes instance because I'll just loop forever. And so that tells me that I probably can't create a yes verifier. That's not a formal proof, but that probably tells me that the emptiness problem cannot be CE. And so, in fact, this is the intuition. The answer is indeed no, but you can actually prove that the answer is no by just saying that it's because the emptiness problem is undecidable. And amazingly, it turns out that if the emptiness problem was undecidable and co-CE, it couldn't have also been CE because then that would actually mean that it was decidable to begin with, which would be a contradiction. And to formally state this, I'm going to present to you the following theorem, which is attributed to Emil Post, who we will talk about again, but who is a brilliant computer scientist. Well, I guess he was a mathematician, but a brilliant mathematician who was really ahead of his time, ahead of even Alonzo Church and Alan Turing's time. And so what this theorem says is that if I'm given some non-empty alphabet and some language defined over that alphabet, then L is decidable if and only if L is both CE and co-CE. This is quite an amazing result. So let's prove this. The proof is going to be more of a sketch, but it'll be good enough, I think, to convince you. The first part, right? The first part, so the if-then is really not that hard. So the if-then is really just by definition, right? So if L is decidable, then it has some Turing machine which accepts it and halts on every string. And so, of course, it's C. And so it also means that L complement is decidable because if L is decidable, so is L complement. So I have a Turing machine which also halts on every string and accepts L complement, so it's also co-CE, right? And so this holds basically by definition. The other direction is slightly more interesting. Slightly more interesting because if L is CE, then let's actually use the enumerator definition this time. So if L is CE, that means that I have some enumerator E1 for L, right? My definition. If L is co-CE, right, remember what co-CE means? It means that L complement is CE. So that means that L complement is CE, which means that I have some enumerator E2 for L complement. Okay, so what does this tell me? Right. So I have two enumerators, right? I have two enumerators. I have E1 and I have E2. Okay. So E1 enumerates strings, right? Enumerates strings. Let's say it enumerates W1, W2, W3, and so on. And each of these strings are in L. Right? That's what an enumerator E1 enumerating L means, right? By definition. So what about E2? Well, E2 enumerates the language L complement, so that means it enumerates strings. It enumerates strings U1, U2, U3, and so on. And each of these strings are an L complement, and all the strings in L complement will eventually be enumerated by E2. So now, remember, my goal is to show that L is decidable. So to show that L is decidable, right, what I need to do is I need to create some Turing machine M, which halts on every string. And if the string is in L, the Turing machine should say yes. If the string is not in L, then the Turing machine should say no. Well, what I can do is I can create the Turing machine such that it simulates E1 and E2, and it can dovetail the simulation, right? And on some input string W, so on some input string W, if W is enumerated by E1, so if W is enumerated by E1, so it's here, then I answer yes, right? So it's here, then I answer yes. If instead W is enumerated by E2, right? So if W is enumerated by E2, so it's here, then I'll answer no. And so now you're thinking, well, how do I know that this doesn't loop forever? How do I know that I don't just wait for both of the enumerators forever? Well, that's because L and L complement partition sigma star, right? So sigma star is partitioned by L and L complement. Right? So that means that E1 and E2 cover all of the space of sigma star, right? So every string in sigma star is going to eventually get enumerated by either E1 or E2, and only one of them. And so this works out. This halts on every input string, and it correctly says yes when the answer should be yes, and no when the answer should be no. Right? Very good. And so that shows that if L is CE and co-CE, I have that L is decidable. Excellent. So the implication of this theorem, so let me put a box because I kind of proved that. I'll post the more formal proof later. But the implication is that we can refine the undecidability hierarchy. I'm going to stop calling it the Chomsky hierarchy because it no longer has to do with Chomsky. So I can refine the undecidability hierarchy as follows. So if I have these two large sets, oh, this is supposed to, there we go. Excellent. Thank you. Okay, good. So I have two sets, and this set is the set of languages which are CE, right? And I have this set, which is a set of languages which are COSI. So in this set, I have languages, right? So this is L1, this is L2, this is L3, and here I have more languages, right? This is L4, this is L5, this is L6, and so on. And so what this tells me, what the previous theorem tells me, is that this intersection here, so this intersection, is exactly equal to the family of decidable languages. So there's no possible decidable language which is either here or here. It must be in the intersection. So all decidable languages are within this intersection here. So these are all the, I guess I shouldn't have shaded this. These are all decidable. Okay. And so let's think about all of the problems which we showed were undecidable, and let's classify them into these two sets. Right? So the halting problem, well, we showed that the halting problem was undecidable. So it's either here, here, or also here, right? Something could be neither CE nor CoCE. In our case, the halting problem is undecidable, but CE, right? So the halting problem would be here. Whereas the emptiness problem is over here. What about the acceptance problem? No one acceptance problem? Ben, come on, you know. Yeah, C, very good, thank you. Right, it's C because how do you check? Well, if a priori you know that M accepts X, then just run M on X. Right. Very good, thank you, Ben. Okay, excellent. And we can sort of continue to categorize each of the problems we saw as either CE, CoCE. But there's also problems, it turns out, that are neither CE nor CoCE. And so, in fact, the EQ problem is neither CE nor CoCE. We won't prove that here. What we're going to prove is we're going to prove that the fin problem is neither CE nor CoCE. So now you're probably asking yourself, well, how do you show that something is neither CE nor CoCE? Is it sufficient to just say, oh, there's not a no instance verifier and there's not a yes instance verifier? Not really, no. So that's the use of a no instance verifier and a yes instance verifier, or at least checking in your head whether or not it exists. That's a good exercise to check whether it's CE or CoCE or neither. But to actually prove this rigorously, we need two rather than just one mapping reduction. Okay. So to show that L is neither CE nor CoCE, we need two mapping reductions. In case one wasn't enough, you have to do two this time. Okay. So you need to use one mapping reduction to show that something is not CE, and you need to use another mapping reduction to show that something is not CoCE. If you have both, then of course it has to be outside here. Okay. And so I'm quickly going to state the theorem that tells us that this is true. And this theorem tells us that if I have two non-empty alphabets and I have languages over both of those alphabets, okay, L1 and L2. So imagine L1 and L2 are just the languages which correspond to two decision problems, right? And I have that L1 mapping reduces to L2. Then what this theorem tells me is that if L2 is CE, then L1 is also CE. And so you're probably thinking, well, what's the connection between this theorem and this line here? Well, just use the contrapositive. Right? And then it tells you that indeed, if you have a mapping reduction and L1 is not CE, then L2 is not CE. So I'm going to quickly prove this. Not going to take very long, I think. Because if I have L1 mapping reduces to L2, then what that tells me is that I have an instance modifier, right? So I have an instance modifier which takes some string in L1, right? It takes some string in L1. So this instance modifier takes as input some string in L1, and it outputs some string, some string in L2. Okay. So remember, that's what it means to have a mapping reduction. It means that I have some computable mapping reduction function f, which starts with some string in L1 and outputs some string f of x in L2. Right. Okay. So I have this, and really the result that L1 is C isn't all that difficult to see because I can just combine this instance modifier with the Turing machine M2 that accepts L2 because L2 is C. So L2 is C, which means that there exists a Turing machine M2 that accepts it. So I can take the instance modifier and then combine it with the Turing machine M2. Right. And so now remember that for L1 to be CE, that means that I have a yes verifier, right? So for L1 to be CE, I need to have a yes verifier. Well, suppose the answer to the input to the instance modifier was yes. Because of the property of mapping reductions, f of x, the answer to f of x is still yes in L2. And so now I feed a yes instance to M2, right? But because M2 is really a yes instance verifier, this will also tell me yes. And so then I can actually answer yes to my initial input x. Right? So that means that altogether I have a yes instance verifier for L1, or really I have a Turing machine M1 for which L of M1 is equal to L1. Okay. And that shows the theorem. That shows that if L1 mapping reduces to L2 and L2 is CE, then L1 must also be CE. And so then by contrapositive, if L1 is not CE, right? So if I have L1 mapping reduces to L2 and L1 is not CE, then L2 is also not CE. And I can also conclude by this theorem. Using the fact that L1 mapping reduces to L2 also implies that L1 complement mapping reduces to L2 complement. I gave this as an exercise, so I won't show why. And so this implies, together with the mapping reduction, that if L1 is not co-CE, then L2 is also not co-CE. So if I have a mapping reduction from L1 and L2, and there isn't a yes verifier for L1, then I can't have a yes verifier for L2. And similarly, if L1 mapping reduces to L2, and I can't have a no verifier for L1, then I can't have a no verifier for L2. That's what this is saying. Okay. And so now actually, before we get to showing that fin is neither C nor co-C, I want to just quickly show you an example, which relates back to Tuesday's class, where we were trying to map reduce the halting problem to the emptiness problem. Right. So if you remember, I was saying, well, trying to map reduce the halting problem to the emptiness problem is actually impossible. And now we can see why it's impossible. We can see why it's impossible because the halting problem is CE and undecidable. So that means that it's not co-CE. So the halting problem is not co-CE. But the emptiness problem is undecidable and co-CE. So that means that the emptiness problem is co-CE. Well, I didn't even have to say it was undecidable. The emptiness problem is co-CE. But now, if I were able to have a mapping reduction HP to empty, then what this theorem is telling me is that because the halting problem is not co-CE, then the emptiness problem should not be co-CE. But that's a contradiction because the emptiness problem is co-CE, right? So this would be a contradiction. So that's why this is not possible. And to answer Louis Tuesday's question, you had asked, well, could you do the emptiness problem mapping reduces to HP? And I was not very confident in giving you an answer. Now I'm extremely confident. Am I? Yes, I am. So the emptiness problem is co-CE, but it's undecidable. So that means that it's not CE. Whereas the halting problem is CE. So it is CE. And so if this were possible, then we would have a contradiction. So this is not possible. So again, a contradiction. I'm glad we could settle that. Okay. So now, any questions about this? No questions? Okay. So now we're going to get to the most important example of today's class. Okay. So today's most important example is the following. It's to show that the decision problem fin is neither CE nor co-CE. So you're probably asking, what is fin? I have a friend called Finn, so that's not this Finn. The decision problem fin asks, given a Turing machine M, is the cardinality of L of M finite? So this is asking, is L of M finite? So this is asking, is L of M finite? So this is neither CE nor co-CE, because if you think about it intuitively, it'd be extremely difficult to design either yes or no verifier. And so to show this, we need two mapping reductions. Okay. So what I'm going to do is I'm going to do two mapping reductions, both from the halting problem. So I'm going to show that the halting problem mapping reduces to fin, and the not halting problem mapping reduces to fin as well. And because the halting problem is not co-CE, then this will show that fin is not co-CE. And because the not halting problem is not CE, then this will show that fin is not CE. So you're probably asking yourself, well, why is the not halting problem not CE? Well, if you had a yes verifier for the not halting problem, then you could use it to decide the actual halting problem. So it turns out that one of these reductions is much harder than the other. So I'll do the harder one. So this one is easy, and this one is less easy. So I will do the less easy one. So we'll do reduction A. Okay. So I'm going to do a mapping reduction. So let's get back in the mind space of doing a mapping reduction. What I need to do is I need to show that fin is at least as difficult as the halting problem. And so to do that, I need to first take an instance of the halting problem and convert it with my instance modifier to an instance of the fin problem. Right, so this is an instance of HP, and this is an instance of fin. Okay. And I need to do that with a particular objective in mind. This particular objective is that M halts on X if and only if L of N is finite. Okay, this is what I need to do. Okay. So this is kind of hard because now if M halts on X, how do I make sure that the Turing machine I create is finite? It's a bit tricky. None of the tricks that we showed so far are going to help with this. We actually need a new, very interesting trick called bounded computation. So in bounded computation, we use the fact that m halts on x. And so the fact that m halts on x means that at some particular time step, m has stopped running on x. So we use the time step at which m halted on x as the bound to the length of the strings accepted by n. So this is the idea, this is the intuition. If m halts on x, then take the time step at which m stopped running on x and use that natural number as the bound, as the upper bound on the length of the strings that n can accept. So that would mean that L of n is bounded. Otherwise, if m does not halt on x, then you can't find such a time step. And so there's no bound on the length of strings in the language accepted by n. This is the intuition. How to do that is a bit harder. Right? So how to do that is with the following block of code. So let me go here. So n will on input w, do something very new. So it's going to do something very new, which it hasn't done before. It's going to store w. It's going to store w. So how can it store w? Well, it copies w and maybe it places it very far away in the table. If that's not far away enough, then it could just place it even further. Okay, so it stores w, and then it loads x. It loads x on the tape. Okay. So it loads x on the tape, right? So now we're back to something that's familiar. And we're going to run m on x, right? Okay, also familiar. But we're going to run m on x for the length of w steps. Okay, interesting. So at this point, it's not super clear how this intuitive idea maps to this this running m on x for the length of w steps. So we'll see why in a second. But before we do that, well, what's the if statement, right? Because I need some kind of if statement to either accept or reject. So the if statement is going to be that if m has not halted on x by time step w, then accept. Otherwise, reject. Okay. And so one of the reasons why this mapping reduction is confusing is because there's kind of like a double negative here. You can just think of has not halted as m is still running. Okay. So now this is the mapping reduction. This is the instance modifier. Now, if I were you, I'd be extremely confused because it's not at all obvious how this implements the intuitive idea I just gave you. So let's see how it does that. Let's first analyze the behavior of n when the answer to the instance of the halting problem was no. So if the answer to the instance of the halting problem was no, then what that means is that m loops on x. Right? M loops on x, right? Never stops running. So if m never stops running on x, then regardless of what w was, if I go to this if statement and I ask myself, is m still running? Right? Is m still running? Then that's always going to be yes. Right? M is always still running. It loops forever on x. Right? So if m is always running, then this if statement always evaluates to true. And so then this then except always executes, regardless of w. So that means that regardless of w, n accepts. So this tells me that L of n is equal to sigma star. The sigma star, last time I checked, is infinite. And so that means that I have a no answer to the instance of the fin problem. Okay, so the no maps to no. Okay, now the less obvious thing is how the yes maps to yes. Okay. So how does the yes answer map to a yes answer? So if the answer to the halting problem is yes, then what that means is that M halts on X, right? So if M halts on X, what that means is that M runs, right? M is running on X. And then at some point, at some time step, it stops. Right? It stops running, and then it never continues to run. Right? So it's halted, right? If it's halted, it doesn't start back up again. So that means that at some time step, let's call it W, M halts on X. Okay. Right? Hopefully, I haven't said anything illegal. M halts on X. That just means that there is some time step where M stops running. So now what I'm going to do is I'm going to plot an integer number line. And this is going to help me visualize the behavior of N. Right. So this integer number line is going to represent two things at the same time. So I have 0, 1, 2, 3, 4, 5. Let's say at some point I have y minus 1, then I have y, then I have y plus 1, and so on. Okay. So this integer number line represents two things. It's going to represent the length of the string W, right, and the time step. So let's just look at the time step for now, right? Let's look at the time step for now, and let's ask ourselves the question, has M not halted, right? So I have a double negative. Has M not halted on X? Or another way to think about this, such that it's less mind-bendy, is M is still running on X. Okay, so let's check, right? At time step 0, M has not halted on X yet. So this is true, right? At time step 1, M has not halted on X yet. In other words, it's still running, also true. And it remains true all the way until y minus 1. Because at y, M halts, right? So at time step y, M has halted on X. And so this evaluates to false. At time step y plus 1, M again is stopped running, right? So M has not halted on X. That's not false, right? M has halted on X. So this is false. And now this remains false forever, right? So now let's consider the other question, N accepts W, right? N accepts W. And let's consider this question for every single length of the string. So if N is given input string W, and that input string has, say, length 0, right? So that string has length 0, then, it's stored in the Turing machine N. N loads X on the tape. It runs M on X for 0 steps. And now it checks, has M not halted on X? Well, the answer is yes, right? M is still running, right? M is still running, right? So this is a yes here. So this if statement evaluates to true. This if statement evaluates to true, so I accept. So W gets accepted. So W gets accepted. And again, it's the same thing. Let's take a larger string size, let's say 5, right? So for a string size of length 5, you store W on the tape, you load X on it, you run M on X for, say, 5 steps. Because 5 is less than Y, M is still running, right? M is still running. And so N accepts W. So N accepts W. So then you have yeses, right? You have yeses to this question all the way until y minus 1, right? But at time step y, m has stopped running. M has stopped running, which means that this question, if m is still running, is false, right? So this if statement evaluates to false. And so then w gets rejected. So it gets rejected for length y. It gets rejected for length y plus 1, for y plus 2, and so on, right? So every other string of length greater or equal to y gets rejected. So that means that L of n is equal to the collection of strings. Let's not use u. Let's use u instead of w, for which the length of u is at most y minus 1. Okay. But if I have a bound on the length of the strings accepted by n, then I have a bound on the cardinality of L of n. Right? So that means that L of n is bounded in terms of its cardinality. And so then I have that the answer to the instance of the fin problem is yes. Okay. I will not do reduction B, obviously, because I have minus 1 minutes. But please remember that I told you that this was the most important example of the lecture. Okay. I can take questions, but you're free to go if you like to leave. Have a nice weekend. Come talk.